Alrighty, folks, one last lecture to tie up this Introduction to Isabelle mini crash course. So now we are on day 4 lecture, and the focus of today will be covering quantifiers. So we saw a little bit of quantifiers in last lecture. We saw for all quantifier, but this time I really want to use more quantifiers and see how actually implicitly we've been using quantifiers plots. So let's start off with a sample lemma. We're going to prove that Q is dense in Q. If you have taken a real analysis course, this may mean something to you. Otherwise, we're going to prove this statement. That for any two numbers, that if we fix two numbers a and b as rational numbers, and we assume that a is less than b, then I'd like to be able to show that there exists, so I typed exists by typing backslash exists, wait a little bit, and then this hint pops up and you can press tab to select it. An x of type rat, right? There exists some rational number x such that a is less than x and x is less than b, that we have something between them, right? Okay, the way that we show that something exists, one way to do it is constructively. So I'll just say that I will just construct a number x that's between a and b, namely the average of them, right? If a is strictly less than b, then a plus b over 2 it will be strictly greater than a, but also strictly less than b. So let's prove that, right? Let's see how we might show that this is true. Okay, so I want to construct this quantity, right? This quantity called average. So the way I'm going to define a variable to hold this average. The way that I'm going to do so is with the let keyword. I'm going to then I'm going to write let avg be equal to the quantity a plus b over 2. Right? And this simply lets me define an abbreviation for AVG. This should remind you a little bit of this thesis keyword, right? This thesis keyword is really just like a, like a predefined variable for what is inside of this shows statement. Don't worry about this. It's just saying that Isabelle has already proven this. We're gonna, prove it from scratch and learn a few new proof techniques. So let that be the average. Right? In order to demonstrate this, show thesis, okay, Isabelle automatically simplified this expression as there exists an x greater than a such that x is less than b, right? There exists something between that. So in order to show this, we must show that both parts of this holds. So I'm going to have the fact about the lower bound, that a is less than the average, and then, well, I can, and here, notice here that Isabelle automatically expands, right, this average variable, right? It's not really a variable, it's just an abbreviation, right? It's a syntactic abbreviation for us to represent this quantity. This will have to use a less than b, and this will simply show, right, by auto, have the upper bound, which is that the average is less than b, again using a less than b by auto, right? And once I have shown that, well, this average is exactly this x right here, right? So, the simple way to do it was just to say, okay, using lower bound, upper bound, right? That of course this quantity satisfied them, so roughly it's it's that x, and this will show you, right, that this works by blast. I'm going to go ahead and comment this out and show an alternative way that you might instantiate this existential statement, to just say that if you can prove that some x satisfies it, then you're done, right? So the way I'm going to do this, I'm going to show a bit of a new syntax. I'm showing a little bit of like an apply script style but I found that it's generally recommended to stay away from these apply style proofs because we prefer the structure language that we've been using all throughout this tutorial. But for this particular one, I really like the way that this instantiates existential. When you're trying to prove an existential statement. So this goes apply rule xi. And this is going to now allow you to instantiate something for x, right? It just has to say that as long as you can find something that's between a and b, that's all the subgoal is, right? It got rid of that existential quantifier. So it's an existential, I believe it's an introduction rule. But okay, so here the syntax for this is slightly different inside of apply script. Just remember this syntax. I found it very nice and convenient, where x is equal to the average. And then you'll be able to see that actually this subgoal now reduces to proving this lower bound and this upper bound, right? And so what I might actually do in a proof is say that, okay, I'll first instantiate the existential statement with the thing that I wanted for, and then I'll just copy paste the statements in for the for the two subgoals that I want to prove, rather than typing it all out by hand, right? Okay. Sounds good. But either way, now at this point in the proof state, you can again use lower bound, upper bound, and it will prove, right? Okay. Same proof, just a more explicit, showing like a more explicit way of how you might work with this existential quantifier. Okay, sounds good. Now, you might say that, well, this is, when you're sort of presenting this lemma to maybe someone with a more mathematical background who doesn't really know Isabelle, it's like, okay, well, what is this fixes? What is this assumes? Why is it all broken up like this, right? Maybe I just want to read one statement, right? Like really the if you're just strictly trying to write this in first order logic over reals, or over rationals, I guess. Lemma, let's call it Q is dense in Q, alternate. Right, we really want to show, say the statement that for all rational numbers a and b, that if a is less than b, then there exists an x, a rational number x, such that a is less than x and x is less than b. Right. This statement is really what we want this to really what we mean. And in fact, these two statements are exactly the same, right? Under the hood, they are exactly the same. I'll show you in a little bit how you might transform it. So, but when you have pure quantifiers, right, the way we can see this is, okay, well, for all statements, whenever you fix, right, something a and b in a proof, just say, okay, let a and b be some fixed arbitrary rational numbers, right? It's a for all quantifier, right? And then when you say that, when you say assumes a is less than or equal to b, right, you're saying that if a is less than or equal to b, then you can assume this conclusion right here, right? Okay, sounds good. And so the way, typically, when you have a lot of quantifiers, I'll show you another proof technique that you can do. We saw induction last time, but inside of this proof setup, you can give it another argument. This one is called clairsimp, where essentially it translates this right here is object language, where it's essentially first order logic, right? And then clairsimp translates it into what's called the meta language. Right, this is the meta language, where this big for all turns into this big and this skinny arrow turned into this big arrow, right? And essentially, when you're in the meta language, you can use meta statements. You can use meta keywords to do these things, right? Like this, for all A and B, we said corresponds to fixes. And the way that you can do that within a proof is you can just say fix A and B, which are rational numbers. Right? And then we want to say that, okay, we can assume that if A is less than B, we can actually just write assume A is less than B. Right, notice there's a little bit of difference. It's fix and assume instead of fixes and assumes, right? But it's very, very similar. That A is less than B. Too many colons. Right? And then we are going to show that this final statement holds. So show that this holds. And then we say sorry, and you can say QED here, right? And this essentially turns this statement into what we were proving before, right? Now, just a word here. This, if you just type thesis, nope, never mind. Forget I said that. But here, right, notice that we were able to assume this statement because it was part of this. It was part of the statement, right? Like if you try to add an assumption that's sort of nonsense, let's call this the nonsense assumption. Let's say, maybe A is equal to B, right? We know that's not true. Here it's going to show you an error, right? It's failed to refine any pending goal. It's saying that the way that you set up this proof does not match the shape of what the meta language expects you to set it up as, right? Okay, good. I don't know yet if there's a way to automatically go from this to that. In theory, I don't think it should be difficult to implement one. I just don't know of a way to do it. I don't know. Someone who's more well-versed in Isabelle maybe can let me know how to, if there's a way to automatically just generate this block from this goal state. But yeah, anyways. And the proof is going to be exactly the same, right? I should be able to just copy paste everything from before, and it should just prove because they're exactly the same statements, right? Okay, wonderful. So now we're going to take a slight detour into polynomials because I want to show off some more interesting examples of involving quantifiers, and to do that we need we want to talk about a little bit more interesting objects. And so if you recall from lecture 1, we imported this thing called computational algebra polynomial factorial. We imported this so that we'd have access to do polynomials now, right? If you're wondering why we imported this particular library. Okay, so going down, we have polynomials. So this particular polynomial library, right, like, if you want to learn more about it, you click into the theory file, and it will tell you all of the different things that you can do, right? So there's this, it imports this polynomial library. That's probably what you would look at to see the base polynomial library. So, it defines what a poly is, defines the degree, defines the zero, right? This is a decently big library of polynomials, right? 6,300 lines worth of polynomial code. So let's go back. Where was I? I think I want to say I was here. Here we go. Okay, so I'll just show off a couple of these simple ones. But essentially, polynomials are represented by their coefficients, right? So when I write, so I'm going to go back to value commands to show off some things. When I write, the syntax for how you work with this particular poly library is a poly of, for instance, it's a list, but in order to say that it's a list of coefficients, right? It's like a special type of list. oh, sorry, actually, the way that you just define a polynomial is a list of coefficients, but it's a special type of list, so the coefficients actually go in between two, a start colon and an end colon. For example, let's say 1, comma 2, where these are real coefficients. This will tell you that this is a real polynomial. And this represents the polynomial f of x is equal to 1 plus 2 times x. Right? Okay. And the way that we can sort of verify this as a polynomial is by taking, is by calling poly on it. Calling poly on this polynomial turns it into a function that we can evaluate. So look here, right? This was a real poly. Now it's a function from real number to real number. It takes a real number as input, outputs a real number as output, right? So we can test a couple of values. Let's say if I input 1, I should get 3, right? This is saying f of 1 is equal to 3. No, is equal to 3. If I put input 2, this is equal to 5, right? F of 2 is 5. I can try one more. F of 3 is 7, right? Okay, so that's polynomials, right? You can, we have functions for finding the degree of a polynomial. For instance, the degree of this particular polynomial is going to be 1 because it's of degree 1, right? The degree of, actually it's even easier if I just inside of, typically what we like to do inside of value commands is just to say what is equal to. If I say this is equal to 3 and say this is equal to 5 and say this is equal to 7, then someone who loads the file again can just click through and say that, oh yeah, it's all true, so you just read what's on the screen instead of having to type this out as a comment, right? As a little bit silly here, but anyways. So the degree of this polynomial is equal to 1. If I add one more coefficient, namely the coefficient, this is 1 plus 2x plus x squared, the degree of this polynomial would be equal to 2, right? That's that this is true, right? And so on and so forth. You can find the coefficient of a particular polynomial, right? For instance, let's say this polynomial, the coefficient of the 0th degree term is 1. It's easier if I change this up a little bit, right? The coefficient of the 0th degree polynomial, 0th degree coefficient is 1. The coefficient of the 1st degree polynomial is 2. The 2nd degree term is 3, right? Equals 1, equals 2, equals 3, right? All of these are true statements. Okay, sounds good. So now let's, build some more interesting examples. So we saw that we were doing a proof where we were trying to prove an where the conclusion was an existential statement, right? We had to prove that something existed. What about a statement where we assume that something exists, right? So we're going to prove a lemma that a polynomial with even power is always positive, or I guess non-negative, right? We're going to say fixes implicitly, right? This is for all polynomials p, for all real polynomials p, where x is some input and n is the degree of this polynomial. I'm going to, sorry, n is not the degree of this polynomial. And we're going to raise this polynomial to some even power, right? And we're going to say that n is even by saying that there exists a number k such that n is equal to 2 times k, right? So i.e. n is even. And what we're going to try to prove is that when you evaluate the polynomial p on the variable x, and you, well, yeah. When you evaluate this polynomial p raised to the power of n on the variable x, that this is at least 0. Right? Okay. Just a note here that this p to the n is a polynomial. Like, it would be the equivalent of if I wrote something like, for instance, 1 plus x squared, right, is actually the polynomial 1 plus 2x plus x squared. Right, this is the statement that 1 plus x squared is equal to 1 plus 2 times x plus x squared. Right, this is taking the polynomial to the nth power and then evaluating it on the input x, right, that this is non-negative. Okay, sounds good. Let's go ahead and try to prove this statement, right? In this case, we haven't done one of these in a while, just a plain old boring vanilla proof block, right? No special proof method setup. And we're going to start off by using this assumption, right? If if n is even, there exists some k. I'd like to get my hands on that k, right? I want to work with this k. So, I want to say something like let k be, an integer such that n is equal to 2 times k. The way we would do that is by obtaining k, where I'll label this as n is equal to 2 times k. And if I say using the, let's call this the n even assumption, using n even, this is a case where you can automatically, where actually a trizero will just do it, right? If you know that something exists, then of course you can obtain it. You don't have to go through a sledgehammer to obtain this k, as we've seen before, right? So now when we're trying to show the thesis, we can sort of do unfolding n is, right? Now this is the statement that p to the power of 2 times k of x is equal to that. This I now want to rewrite in a slightly different way, that p to the power of 2 times k is really, well, I want to say that when you have poly of p to the power of 2 times k of x, it's really the same as saying if you evaluate p to the k of x and then raise the whole thing squared, right? What I want to say is that this right here is equal to, you can first evaluate poly of p of x. Well, okay, I mean, even simpler, that you can just evaluate the polynomial on x and then raise the entire power to 2k, right? This might be an even easier statement to at least say. Let's see if this try-zeros. Good. Simp is able to find that this is true. So we're going to say, let's call this, I don't know, polypow, polynomial power. All right. So we'll unfold polypow as well to see that now the this power is getting pulled outside of the polynomial evaluation. So now it's a real number to the power of an even power, right? And this is greater than 0, and I wonder if this will just prove. Yeah, right? That proves automatically, right? Anything to an even power is non-negative, of course, right? So there you go, right? We saw that if you have an existential, right, then of course you can obtain such a k. Right. Okay, sounds good. Now we're going to do one last example that's a little bit more involved. So I'm going to write a definition here. I'm going to write a definition called roots, which takes a real polynomial and it returns a real set, where the roots of p is defined as the set of all real numbers x such that p of x is equal to 0, right? This is very clearly the definition of the roots of x. Okay, good. What we're going to show is that the root of a degree 1 polynomial is it has exactly one root in its closed form. Right? So we're going to say fix as p is for some real polynomial, and we're going to assume that the degree of p is equal to 1. And then we're going to try to show that the roots of p is, we can express this in terms of the coefficients of p, right? So that if p is some polynomial a plus bx, then the root is equal to negative b over a, right? So it's negative of the, a over b, cannot do algebra today, is the negative coefficient of the 0th degree term of p divided by the coefficient of the 1st degree term of p. Right. Okay. Sorry. Greedy, right? And this might already be, be a more interesting proof, right? This will, it has a bit of some more interesting things. So let's think how we're going to do this, right? So first of all, one of the very first things we said was that, well, if p is equal to 1, then we should be able to write p in some way, right? Like we should be able to represent p as some with some coefficients a and b. So let's just try to do that, right? Let's just try to obtain these coefficients. So we'll obtain a and b where p is equal to the polynomial ab, right? Where these are the coefficients. These are real numbers, right? And we are going to use, let's call this assumption degree 1, right? We're going to use the degree 1 assumption, right? If we didn't have this degree 1 assumption, we wouldn't be able to write this. If it's degree 0, well, it actually doesn't let you, hold on, sorry. One more strict thing, and b is not equal to 0, right? It's not degree 0. It's not a degree 0 polynomial, right? That its first degree term has a non-zero coefficient, and it doesn't have any higher coefficients, and this should be /hammerable. Good. In degree 1 coefficients. This is probably already a lemma that's saying, yeah, right, that exactly what we were trying to prove here. Good. So then we have that b is non-zero. I'm going to go ahead and label these facts. This is p rep for p's representation as coefficients, right? And then this is b non-zero, saying that b itself is non-zero. And then I'm going to want to say that, well, if I know how to evaluate, that if I know the coefficients of p, then I know how to evaluate p, right? Like I want to say something along the lines of like that. Okay, if you know how to evaluate, if p is equal to, I should really say p of x is equal to a plus bx, right? Then the only way to make p of x equal to 0 is when a plus bx equals 0, which is, solve that linear equation, right? That's more along the lines of where I'm trying to go. So I want to say something along the lines of that for any input x, that poly of p evaluated on x is equal to a plus b times x, right? I want to say that this is true. Well, so let's say I should say unfolding p rep, right? And let's see if this will work. Good. Yeah, we're automatically able to solve this, right? Okay, sounds good. And then now the actual thesis that we're trying to show is that the roots of P is exactly equal to this set, right? So I'm going to go ahead and say unfolding roots def, right? The definition of roots is that it's the set of all x's such that P of x is equal to 0. So now our goal turns into trying to show that this set is equal to this set. Which is essentially this statement. You could either show it by double inclusion, but double inclusion is just an if and only if statement that poly P of x equals 0 if and only if x is equal to this fact right here, right? I'm going to go ahead and just prove that these two coefficients are equal to a and b. So I'll say this is C0. Coefficient of P at 0 is equal to a. Using p rep, right? To try to, I want to make this a little bit more simpler to see. Have C1, the coefficient of P, the first degree term of P has a coefficient of B. Using p rep again, right? Should be the same proof, right? And then now in here, I can try to unfold C0 and C1, right? All we're trying to prove is that x is equal to 0. That P of x is equal to 0 if and only if x is equal to negative a over b, right? Okay, good. And so we're going to do exactly that. We're going to write exactly that, right? That poly P of x is equal to 0 if and only if, right? This is how you type it, arrow dash dash arrow, x is equal to negative b over a, right? And this, we want this to be quantified for all x, right? That for any arbitrary x, P of x equals 0 if and only if x is equal to negative b over a, right? Otherwise, we don't have. Otherwise, this x is like an unqualified variable. Okay, sounds good. So now we are going to use this statement, right? This is p eval. This is a way that we evaluate p using p eval. And you'll see here that, you know, this goal, I first want to make sure that this sub-goal actually helps us solve this root, solve this final thesis. So if I just type then show, right, I want to make sure that this sub-goal is something that's useful. I'll go ahead and just apply sledgehammer here. Hopefully that will do it. Oh, sorry, I wrote b over a. It should be a over b. That's why I was having trouble. This should now work. Good. That shows very simply. Okay, all right, so in general, it's good, you know, if you identify something that you think is a sub-goal, make sure that it actually solves the remaining goal downstream, right? So that you can just focus on this. You don't want to be like, oh, you wrote something, some intermediate step, and then later on you're like, wait, it doesn't actually help you solve the final goal, right? So just make sure that it helps you solve the final goal before you go too far into it, right? Okay, cool. So here, right, we're trying to prove a statement about this for all x, right? But it's just all this really is we're just trying to prove something about this quantifier. And we saw before that ClairSimp helps you turn this into like a more Isabelle proof-friendly style, right? Format, right? So what we can do is we can actually start a ClairSimp proof inside of this, and you'll see that this is, you know, now turns into that meta for all. So we can, you know, fix this x, and we can show that this is true. We'll say sorry, and we'll say QED, right? Okay, sounds good. Here you can immediately just start using p eval, and I think this will probably just do it. I'm gonna go ahead and just show that. Yeah, I'm gonna go ahead and just let Sledgehammer finish this off, and then I will show a more explicit way of breaking down this proof to show the bidirectional proof. So yes, Sledgehammer is able to find it, right? It's able to find a rather large proof, you know, showing off Sledgehammer a little bit, right? It's pretty good. But the way that we might break this proof down a little bit more is to say that, well, we're trying to prove an if and only if statement, right? You should read this equal as an if and only if. In fact, it automatically parsed this if and only if into an equal sign. Syntactically the same thing. We want to show two things, right? We want to show that, first of all, that poly p of x equals 0 implies that x is equal to negative a over b. Call this the forward. I'll do that, right? And then we'll have the converse, that if x is equal to negative a over b, then poly px is equal to 0. Right, and using the actually this was all part of the same proof, right? I'm now showing a more manual way of tackling this proof because I want to show off a few more proof techniques, right? Is that if I use forward and the converse, you know, it's a bidirectional proof, so of course it proves the implication, right? And now we get to work on each of these on its own. So in the forward direction, right, notice that I purposely typed the meta level implicator because I want to actually turn this into its own proof block. And I want to assume, right, when we write this you know, meta level implication, we get to assume that this is true. Let's say that poly px, right, thing is 0, and we have to show that x is equal to negative b over a. Right. Okay. Good. Well, we know how to evaluate the this polynomial p on x, right? In fact, I'm actually going to go ahead. I'm going to go ahead. Well, it's okay. Right, we know how to evaluate this p on x. This orange x is different from this green x up here, right? Like if I say using p eval, right, you have to be a little bit careful. Ooh, that was x. If I say using p eval, right, this green x is universally quantified. This orange x is the x that we fixed in this case, in this forward case of the proof. They are different x's, right? But I'd like to say that right, that using poly px, right, that this poly px just automatically turns into a plus b times x, right? The way that we can do that is we can actually to more easily, you know, like it's almost like I want to instantiate, right, this this universally quantified statement about p, about x, right, about p of x. I want to instantiate this green x with that orange x, right? Because if it's for all x, I should be able to use that orange x, right? The way we can do that is actually change this original statement. I'll go ahead and prove a new one just for the sake of demonstration. P eval, let's call this alt. How about let's call this meta, because we're going to change this into a meta quantifier. Instead of this for all symbol, I'm going to use the meta for all symbol, which is this big and, right? and they're the same, right? They have the same proof solves them, except we can use this meta statement in a bit of an easier way. Here's what I mean, right? Here, when I'm using p eval, right, that has the for all statement, but when I use p eval meta, notice that it doesn't show the for all quantifier, but it shows this question mark x's that you can now instantiate things into, right? So I can instantiate this question mark x, which used to be the universally quantified green x, right? I can instantiate this x as this orange x. So I'm going to do exactly that, right, of x, right? And now it's able to tell me that, okay, yes, you have this fact, right, that you can directly plug something into. To universally quantify the statement, right? And then instead of saying using, I'm just going to say using this, I'm just going to say unfolding this this p eval statement, right? That if I know a plus b times x equals 0, then x is equal to negative a over b, right? In order to solve this equation, you have to subtract a, and then you have to divide by b. So you must know that b is non-zero. So if I use that, using b is non-zero, let's see if this is able to get it. Oh man, maybe it needs a sledgehammer yet again here, just to solve the algebra. Okay, good, right? And this gives us a little bit of a simpler proof from what if found from before, because it had to roll all the steps together, right? But right, so it's able to do the algebra and figure this out, right? But yes, most of the time, right, when you have a statement about something for all in the middle of a proof, to work with it, you probably want to turn it into a meta quantifier so that later on in the proof, you can just very easily instantiate it with whatever you want. Okay, good. Right, and and then here, right, we can do the same thing. Proof, show thesis, REQED. We want to assume that x is equal to negative a over b. So assume, let's call this x is, right? And we want to show that p of x is equal to 0. So first of all, we can unfold x is to say that actually it's poly p of that, right? And then we can again use the p eval meta, right? So using p eval meta, it gives us a way of directly instantiating this x, right? We could instantiate this x directly with this this quantity, and it would do the trick. You could also just let Isabelle's automatic pattern matching do it. So I'll show it both ways. I want to be explicit here, right? You could say of this quantity, and now this quantity exactly matches this quantity. So you would be able to turn this using into an unfolding, and it's just a plus b times negative a over b, which is negative a, so that's a minus a, which is 0, right? But you don't even have to do that. You can just let Isabelle do the pattern matching and say unfolding p eval meta, and it will just it'll just know, right, how to instantiate that. This will probably we need to know that b is non-zero. And it will be able to automatically prove that, right? Okay, sounds good. Yeah, and so we've demonstrated, what happens when you're trying to prove something, right? When your prove goal has has a for all statement, right? Use clear simp, and you're able to fix a particular x to work on, right? What happens if you have an assumption that has a for all statement? Well, typically it's pretty useful to turn it into a meta statement so that you can use that for all statement easier because you're able to freely instantiate it with anything that you want. Right? We saw what happens when you have an assumption that has an existential quantifier. You just use the obtains, right? You just write obtains, and you're able to obtain, the thing that the statement says exists, right? And then at the very beginning, we saw what happens when you're trying to prove a statement about something existing, right? You just have to demonstrate that this works. The one thing that I didn't quite touch on is, another way to show that something exists is to assume it, do a proof by contradiction, right? Assume that it doesn't exist, but maybe I'll do another video on that. later on as a bonus or something, right? But for now, I think we have a pretty good grasp of really how to work with the most fundamental parts of Isabelle HOL, of quantifiers in Isabelle HOL, right? Okay, sounds good. This is a good place to stop.